Our topic of discussion for today is simple harmonic motion. So there are two types of simple harmonic motion. When we have a circular motion, such as this one, it creates a type of wave, just like the sine and cosine wave we've been studying. The second type is when we have some kind of weight or ball attached to a spring, and we can pull it down or push it up, and the spring starts to move. At rest, this line here is called our at rest position or the equilibrium point. Anything below it or above it is considered a displacement. The type of motion is called an oscillation. So what is the definition exactly for simple harmonic motion? It starts with an object that moves on a coordinate axis is in simple harmonic motion. Oops, misspelled. If its distance from the origin D at time t is given by D equals A cosine omega t, or D equals A sine omega t. We call A, our displacement, our amplitude. So the motion has amplitude A, absolute value A, just like we've seen before, and this is called the maximum displacement. Then we have a period of the motion, which is found the same way the period is when we were graphing sine and cosine. And the period is 2 pi over, in our case it's no longer B, it's an omega. And in regards to the motion, what does this mean? Well, the period gives us the time it takes for the motion to go through one complete cycle. So there's two equations, cosine and sine. How do we know if we're going to use cosine, and how do we know if we're going to use sine? It's actually quite simple. We're going to go back to that idea of what the graphs of sine and cosine look like. So let's recall the graphs. This is the graph for sine, and we'll call it t because this is our time. And this is the graph for cosine. This horizontal line is our resting point, our equilibrium. So let's draw some kind of conclusion when to use what. If I notice right here, my time is 0, and it's at rest. So that means at time 0, the object is at rest with a distance of equal to 0. Over here on cosine, however, at time equals 0, right here. My point is up here, which means I am displaced at the very beginning. So the object, I'm going to call this A. So the object is displaced, and D is equal to some value A. So let's take this information and write an equation. A ball on a spring is pulled 4 inches below its rest position and then released. The period of the motion is 6 seconds. Write the equation for the ball's simple harmonic motion. So what's given to me? Well, I know the period is 6 seconds. And I know I'm displaced 4 inches. I have to decide if I'm going to use sine or cosine. Let's go back and check. I'm displaced 4 inches. So here it says the object is at rest. Here it says it's displaced. Therefore, I'm going to use cosine. So I know what the displacement is. It's 4. Now I just need to decide, what is this omega? Well, I know that period is equal to 2 pi over omega. The period is 6, so I'm going to write it as 6 over 1 just to help. We can cross multiply. 1 times 2 pi is 2 pi. Omega times 6 is 6 omega. I want to know omega, so let's divide by 6 and reduce. 2 pi over 6 reduces to pi over 3. My displacement is the absolute value of A. In this case, it's 4. Now we got to think, Is it going to be positive 4 or is it going to be negative 4? Because it is the absolute value. So here's a ball on a string, or spring, sorry. Here's the rest position. It's saying I'm pulling down 4 inches. Since it's being pulled down, this is going to be negative 4. Therefore, A is negative 4. If we had pushed it up 4 inches, it would have been positive 4. But in this case, we started below the resting point, so it's negative. I have omega, I have A, that means I have an equation. D equals A, which is negative 4, cosine. Omega, we found to be pi over 3, and then T. There is the equation for the simple harmonic motion of a ball that is pulled 4 inches below a resting point and with a period of 6 seconds.